In this video, we're going to introduce the idea of Hess's law. What is Hess's law? Well, it's basically a way to determine the delta H of a reaction without needing to actually experiment and do that reaction. Some reactions are actually very difficult to contain and process and make happen. And yet, we still would like to know the energy for them. How can we go about doing it? Well, it all comes down, thankfully, to the fact that delta H is a state function. Remember that the path by which you get to a value for delta H is irrelevant. It only cares about the difference from start and end. When we reorganize these atoms, it doesn't matter how they reorganize. As long as I started as a carbon solid, an oxygen gas, and I end as a carbon dioxide gas, any raises in energies or lowerings of energies are going to balance each other out to the amount that is different for starting and end. How we can do this is we can actually use other reactions. We can take known reactions that we have obtained elsewhere. Let's say carbon solid plus half a dioxygen gas, so half a mole, makes carbon monoxide. And somebody has done this. They've experimented, and what they found is that the delta H naught for this reaction is minus 110.5 kilojoules. Introduction, delta H naught of a reaction. This is a standard enthalpy of reaction. This means it was done at standard pressure, standard temperature. All the materials were in these states as written. If you have that set up, this is the energy that reaction will give you. Delta H naught is just a symbol to say that it was a standard set of conditions. If you are at different temperatures or different pressures, it will slightly alter your enthalpy. And so 25 degrees Celsius, 1 atmosphere, is where most of these values are recorded for. But somebody has gone and done this experiment in the past. So we have this value available. Well, it does involve our starting materials, but it makes a different product, so this really isn't useful on its own. But where it becomes useful is that there is another reaction we can find that says, hey, carbon monoxide gas plus 1/2 O2 gas makes carbon dioxide gas. This has its own standard enthalpy of minus 283.3 kilojoules. Well, this makes the product we want, but it starts from materials that we don't start with. At first, this might seem kind of unnecessary and unuseful, but if you combine these equations, what you actually find is a path to make our products. Literally, add them together. There is a left side of the arrow, and there is a right side of the arrow. List them as such. Carbon solid plus 1/2 O2 gas plus CO gas plus another half O2 gas. That is our left side. We have merely combined these two equations. On the right, CO gas plus CO2 gas. Well, if you think about any equation for algebra and the like, if you have two of the same thing on the same side, you can usually add them together. 1/2 x plus 1/2 x on this side is really just, well, 2/2x. It's a full x. I have half dioxygen and half dioxygen. So what I really have on this side is a full dioxygen, just an O2 gas. Additionally, I have carbon monoxide on both sides. If you ever had x plus y equals x plus z, well, you can subtract x from both sides and end up with y equals z. If you have something on both sides of an equation, you can cancel them. One CO2 on both sides will cancel out. What I'm left with afterwards, if we consolidate at the bottom, is a carbon solid on the left. There's no matching on the right to cancel it. There's a full O2 gas on the left. And that's it. We've canceled the carbon monoxide. The arrow goes to the other side, and all that's left is CO2 gas. We took two different reactions, and we were able to combine those reaction formulas, and what we get out is the formula we originally wanted. Well, if you do the same combination with the energies, what you will get out is the combination of those energies, which will be the delta H for the reaction that we got out by combining the reactions. So negative 110 plus negative 283 is going to be negative 393.8 kilojoules. This is the delta H of reaction for our original, minus 393.8. If you have a reaction and you want to find its enthalpy, but you don't have it readily available, if you can find a series of other reactions who, when you sum together all the things on the left and all the things on the right, and then cancel anything that needs to be canceled from both sides, if when you sum those two reactions together, you produce the reaction you want, making the same changes to the enthalpy by summing them together will give you the enthalpy for that reaction. What this really is treating balanced reactions as reaction equations, as algebra. Equivalent examples here would be x plus 1/2 y equals z, and z plus 1/2 y equals q. Well, if I know what z is, I could plug all of this in for z. And so instead of z here, you could have x plus 1/2 y plus 1/2 y equals q, which just comes out x plus y equals q. Effectively, this is the same setup that we started with. Carbon solid was x, oxygen was y, CO2 was q, and CO was z. We have used our balanced reactions as equations, and we can simply reorder them like algebra. The net effect is whatever it took to rearrange and combine those equations, we do the same to the energies, and the answer that we get, if we get the equation we want, the sum of the energies will be the energy for that equation. Let's do a short practice. H2O2, liquid. So hydrogen peroxide goes to H2O, liquid, plus 1/2 O2 gas. We're going to be told H2 gas plus O2 gas can make hydrogen peroxide liquid with a delta H naught of minus 188 kilojoules. And B, H2 gas plus 1/2 O2 gas can produce H2O liquid, with delta H naught of minus 286 kilojoules. Our question is, what is the delta H of reaction? Well, to start with, we're going to have to modify these reactions a little bit more than in our last example. I have hydrogen peroxide on my left. I can't simply add these two equations and make that happen. If I add these, I'll get hydrogens on the side, and I'll get oxygens on the left, and I'll have hydrogen peroxide over on the right. I have to modify these. I have to rearrange my equations. What I really need to do is flip A around. If I want hydrogen peroxide to be on the left, I need an equation that has it on the left. Well, you can write an equation backwards. There's nothing to stop you saying, hey, let's reverse, so I'll call it negative, let's reverse A. What if it's H2O2 liquid going to H2 gas and O2 gas? Well, there's going to be a delta H for that. It's also going to be reversed. 188 kilojoules. If you do the opposite reaction, you have the opposite energy. All we did was flip A around, but that now gives us hydrogen peroxide on the side we want it to be on. Well, water, we wanted water to be on the right. And the only source of water in any of our equations already has it on the right. And so B looks like it's going to give us the water where we want it. So let's just try and combine them. Instead of the original A and B, which wouldn't combine to what we make, what happens if we have B and reverse A? Well, in this case, if we want to add them up, we will get an H2 gas. We will get half O2 gas from B, and we will also get H2O2 liquid from the reversed A. We then have our arrow, and we add up everything over on the right side. Well, B gives us water. Reversed A gives us H2 gas and O2 gas. If we then go and look for anything that's on both sides, well, there's a H2 on both sides. So we take an H2 off of both. There is half of O2 on the left and a full O2 on the right. So minus 1/2 O2 minus 1/2 O2. We will cancel the O2 on the left, but we don't get rid of all of it on the right. If I then combine these, what I'll find is all that's left is H2O2 liquid on the left, a water liquid on the right, and half O2 gas on the right. We've succeeded at recreating the equation we wanted to be talking about. We then simply have to sum up our energies. We flipped A, so the energy became flipped. We left B just how it was. So my goal now is simply to sum these two energies. Negative 286 plus positive 188. For a total delta H of reaction of negative 98 kilojoules. The delta H of reaction for hydrogen peroxide breaking into water and dioxygen is negative 98 kilojoules. This is favorable. Hydrogen peroxide is unstable. This is why it's so good for cleaning wounds and disinfecting things. It breaks apart fairly easily, and usually in the process can destroy a lot of stuff. But here's how we could use two other equations, reorganize one of them, such that when I combine the reorganized and the second equation, B, I was able to create the target equation. I was able to create the hydrogen peroxide breaking into water and half dioxygen. This is the idea of Hess law. We can reorganize other equations in order to create our target equation. In doing so, we can reorganize the energies of those known equations to find the energy of our target equation.